Hello everyone, today we'll talk about the solution to the problem Stone Game 2. Feel free to pause the video and read the statement and we'll talk about the solution. The first thing that we should typically do when it comes to a game theory problem is to make sure that the rules and specifically the strategies of the players are well defined. Because we have this weird thing, assuming Alice and Bob play optimally. Maybe you've never even seen that statement before. And how do we assume that they play optimally? And there are, of course, many philosophical problems. For instance, if Bob knows that he will lose, then what moves should he make in that case? If two moves lead to the same outcome, what move should he make? It's not really defined. But at least in this case, our game is a zero-sum game. And it's easy to see why. That's because when we have all the stones in all the piles, then at the end, stones from every pile will be either in one player or in another player, so the sum of the scores of both players are the same, and that means that the moves that maximize your score are the same as the moves that minimize the opponent's score. So at least you don't have to worry about making some move that sacrifices something from you, but takes away even more from your opponent. That's not true. If you sacrifice something, your opponent gets it. If you get something, that opponent loses it. And typically in that case, the strategies are pretty easy to think with. I mean, of course, the problem is to come up with the strategy, or to calculate the result, but at least it's pretty clear what each player wants to get. Now another thing that we always want to take stones from the left. You might think of stones. I typically think about those things like a card game, where cards are in a row and we can take cards, and cards are worth something. And at any position in the game, there are essentially three pieces of information that we need. Those three pieces are, so when we have our cards, is the position, so all those cards are taken away, is the turn for Alice or Bob, that's also another piece of information, and also the range, so how far we can go. So this is this parameter that starts as 1, and whenever somebody makes a big move, then that parameter increases. And we cannot exceed twice that parameter. And as is typical in those zero-sum games, well, I don't know if it's technically zero-sum, or maybe it's constant sum or something, but I will be saying zero-sum in that meaning, is that we don't really have to think about this portion of the information. That's because of that zero-sum nature, the moves that Alice or Bob will make at any position are exactly the same. So if it is now your move, but instead it was my move, I would make the same moves to maximize my score as you would to maximize your score. In which case we don't really have to remember whose turn it is, and only calculate the best solution for a player that starts in that position with that range. So we only have two dimensions: positions, which goes from 0 to n, and also the range, which goes likewise from 0 to n. And finally, to calculate the best moves, we should probably find a way of doing that using dynamic programming that will go over all the n-squared possibilities here, and that will solve our problem. And in that case, we'll do dynamic programming using memoization, so not tabulated but the more simple way of thinking about it. And we'll be going through all the positions, trying to see what the best score we can get from that position. So, assuming that we have the sum of all the remaining elements from here to the end of the table, we can calculate it because this is just typical suffix sum. So we start with 0, we add all the elements going backwards, and at the end we reverse the whole array. Now, having that, all the remaining stones that can be taken is just the suffix sum at our position. Can we take all those stones? Well, we have to check if the previous range is such that if we take at most twice as many piles, we'll take everything. In that case, we just take everything and we're happy. Otherwise, we'll take something, progress the position to the right, and now we will get some score. And the score we'll get is, we'll take everything, however, then it is the opponent's move, and maybe that opponent will take away some of the things that we assumed that we take. In which case we add some values. So for instance, we take this portion, we assume that we've taken everything, but the opponent takes this portion, and he assumes that he's taken everything, and then we take this portion. In that case, we have added this thing to our result two times, but an opponent has also added it once, and also we've added this portion to our solution once, when we're starting here, but the opponent has also added it to his solution once, so we, at the end, have exactly the sum of those two red portions, which is exactly our score. So this is essentially an implementation detail that it's easy to calculate the score based only on suffix sums. If it's still not that clear, then just imagine, as I mentioned, how many times you will add all the elements that you take and how many times you will add all the elements that your opponent takes. This is indeed the score. So we can just subtract the best score that an opponent can get from that position. So we can take some number of stones from 1 to 2 times our previous range inclusive, so we have to add 1 here, because by default the end is not inclusive. And after we've taken, so imagine we take all the elements, now it is the opponent's turn. Of course we don't remember it here, but to mark that it's the opponent's turn, we'll subtract their move. So he starts at position plus take, and maybe his range is larger if the number of elements we've taken is larger than the previous max elements taken. And since you want our opponent to get the worst move possible, we'll take minimum over all of those. So you want to put the opponent in a position where his score that he gets is completely minimum. And this is the score that we can get starting at a given position, and of course we want to finally calculate the value when we start at the beginning. It is our move, and our current range is equal to 1.